So in Chapter 2, we've already started taking a look at how systems of differential equations can be examined. And we realized pretty quickly that not all systems are easy to make sense of. So we're going to start by kind of recapping with a relatively simple, straightforward system. So in this system, we have one equation that's the derivative of y with respect to t, and that's v. So a pretty standard derivative of y with respect to t, that's velocity. And dv dt, the acceleration. In this case, acceleration is just a function of position, like the opposite of whatever your position is. So it turns out that when we took this system and turned it into a phase plane plot, a DE plot, with an initial condition, we got a graph that looks something like this. Now, keep in mind, this is one particular solution on the phase plane. So if you remember, this was our initial condition right there. Our IC, in this case, was equal to an initial y, comma, an initial v. And for this one, it was just something really simple like 1, 0. And you can tell it's 1, 0 because we're 1 unit in the horizontal and 0 units in the vertical. Remember, the phase plane doesn't represent reality. Like, it's not a picture of what you'd see if this were an object moving. You're actually seeing position in this direction and velocity in this direction. So you're actually seeing two important pieces of information at the same time. You're seeing the initial position at the same time as the initial velocity. And so this is what we call a solution curve. That's for a particular solution. And it relates back to this differential equation system because back over here, we were talking about, in this particular case, a very simple situation. It's a very simple harmonic oscillator. And in this particular case, we're talking about the motion of just a mass on a spring, kind of moving on a frictionless surface. So this is about as simple a motion problem as you can make. And it turns out that you can kind of break down the graph on the phase plane. You can kind of take a look at each one of the variables separately because there's more to it than this. This is the position and this is the velocity, but there's another variable, of course. There's time. Each one of these are functions of time. And so you can take a look on the y versus t or v versus t graphs, and you can see there's two different things. And we were able to make this in our Maple document. We were able to make these by using the scene command. So remember, this is like the phase plane. Remember, that's our DE plot in Maple. And if you wanted to be able to see these variables separately, you wanted to be able to graph those separately, you'd use the scene and either something like t comma y or scene, and I'm going to put quotes around this because that's the command, or scene equals t comma v. And we're going to see this in a Maple document here in a second. But what we're actually seeing in this case are two graphs. These are the two graphs, the position graph and the velocity graph with respect to time. And these are really parameterized. That's a fancy way of saying it. These are parameterized view of our solution. So the solution curve up here, when you take a look at each one of its component parts, the position and the velocity, looks like this. And so what we're seeing are the y of t and the v of t. They're both the dependent variables, graphed versus the independent variable. So let's take a look at what this might, oh, and just to kind of make sure we see, the initial velocity, excuse me, the initial position is 1, and the initial velocity is 0, and that's when the t equals 0. So you can see that this really does represent the exact same location. This location on our graph up here, this initial condition right here, we can see in these two places, here and here. So let's take a look at what we're able to do in Maple and see how that works. So I'm going to switch over to Maple here real quick. And so in Maple, we know that we can start with a system of equations like this. And this is just me typing in the system. And I'm going to refer to them as EQ1 and EQ2 just for simplicity's sake. And I can solve that system by doing a desolve. And so Maple gives me the general solution. There's the general solution for the V, and there's the general solution for the Y. But right now, the solutions aren't nearly as interesting to us as the fact that we can also make the phase plane. And the phase plane for this really is just a picture of what's going on. And you'll notice the arrows on the phase plane tell us what direction our solution curve has to travel. Just like in the notes, you can see that the solution curve has to travel in a excuse me, clockwise fashion. And that's because this is position, the direction of position, and that's the direction of the velocity value. And so I added an initial condition 0, 1 up there. And so adding the initial condition allows us to see that. The other thing that's worth noting is I gave it a time unit of 0 to 2 pi. Now, if that sounds strangely familiar, like, hey, 2 pi, isn't that like once around the circle? Absolutely. And if instead I were to change this from 0 to 1 pi and see what happens, we would have, after Maple decides to make my graph here, we would have half of a circle. It starts here and goes 1 pi unit in time. It needs to go the full 2 pi to make it all the way around. So back in the code, I can change that to 2 pi. So some things that you would kind of expect to happen on that phase plane do. And you can play around with the settings for time to kind of figure out what's going on. Notice I also gave it a title so that I'd be able to refer back to this, or if I wanted to grab this graph, it makes sense later on. And don't forget, you can also resize the graphs. So if you really wanted to resize the graph, make it bigger, easier to read, or easier to see, you can do that as well. So we were able to make this DE plot, and by just tacking on one extra chunk of code, we're able to make the scene graphs. And these are really just the same thing that's in the notes. You'll notice in the first one I did, this is V versus T. So this is scene T comma V, and I'm able to make the graph over a full cycle from 0 to 2 pi. And I made them different colors to make it a little bit easier to see. But I'm able to do that for both the velocity as well as the position. And that's just by changing the scene component here, right? It's the same code, it's just one subtle change. Now, what's nice about Maple is that it allows us to do this pretty quickly and easily, but we got to be able to remember that in the end, all three of these representations are really telling us the same thing. This is the system in terms of equations. This is the system on the phase plane, but it's really one solution for the system. And this is what one particular solution looks like. And we can put all of this together because we don't think of just these two variables. We think of this third variable, time. But since these two directions are already spoken for, the time variable must be coming up and out, towards the camera, up and out of the page. And so if you imagine this thing moving on the phase plane, it doesn't stay on a flat surface. What it's actually doing is it's moving up through time, and what we see is sort of the compressed, flattened view of this. So down at the bottom of this page, it kind of pulls all this stuff together here. And it's worth spending some time on this to really try to visualize what's going on. We have two of those scene graphs that we might have spotted here. This is a scene graph, and so is this one. So if you just cover up everything else and just take a look at that, that looks an awful lot like one of the scene graphs that we spotted before. Same thing over there. That's just the velocity curve. That's the position curve. And if you look at the bottom of the page, what you're actually seeing is the phase plane. So this thing down here, that representation, this box down here, this plane, really is the phase plane. And you'll notice that that's just our standard DE plot, right? Oops, DE, capital E plot. And so we can create this, which is really just a shadow down the time axis. It's a shadow of the actual curve. And the actual curve, the thing that we're looking at right here, that's kind of like a corkscrew moving through space, that's the actual three-dimensional representation of what the real system looks like. This is, we can get to it by doing a DE plot 3D in Maple. And it uses the exact same code as a DE plot. It just has that extra 3D at the end of the command. And what you're seeing here is literally what happens to the position, what happens to the velocity as we move through time. And so the solution curve for the entire system, I'm going to make a little note here, the solution curve for the system on the phase plane is just a shadow, or as we would call it in mathematics, a projection. A projection of the entire curve. Oops, I want to say in 3 space down onto a 2-dimensional plane. Right? So the 2-dimensional plane that we're talking about here, that's what we would call the YV plane. Oops, YV plane. Right? So the entire curve is moving in 3 dimensions, Y, V, and T. And if we just project that down onto the 2-dimensional plane, we're able to see the phase plane. In much the same way that we took the slope fields from chapter 1, and for an autonomous differential equation, we were able to compress an entire plane into a line, and we called that a phase line. We can now take an entire space, an entire 3-dimensional space, and compress it down onto a plane. That's what we're doing in this section. So let me hop back over to Maple just so we can see how that works in terms of code. If we use the code DEplot3D and then pretty much everything else the same, we create over one full period, 0 to 2 pi, we create a 3-dimensional curve that rotates. And it's a little sluggish because my Maple's a little sluggish. But if I twist it just right, you will see an image that should look really familiar, right? That's the phase plane. That's 0, 0 is right in the middle. And that is nothing more than the phase plane graph. So in a way, we're kind of staring straight down the time axis. So you can't see time in this graph anywhere. The only way you could get a sense of it would be being able to kind of manipulate how far around this curve goes. But if I rotate this 3-dimensional graph, then you get a sense of, oh yeah, it is moving in time. And so if I shift it and I twist it around and I get this thing to just the right point, you can see what does it look like in the TV plane, or excuse me, the VT plane, right? This is time in this direction, and this is velocity in this direction. And if I rotate it again, keep my time axis the way it is, and I get Maple to behave properly. Come on, Maple. It's a little sluggish for me right now. I think I'm doing some processes in the background. So unfortunately, my Maple is being really stubborn today. So if I try to grab this thing and twist it, it's not working. But nope, it's starting to go. So eventually, once it rotates around, we'll basically change the axes so that we still have the time axis, but now we'd be looking down, being able to see the position. And you can see what happens to the curve. If you do it on your Maple, you'll be able to spot it too. You see what happens to that curve, and it's all coming together. And that means that we need a way to be able to write, and I'm going to switch back over to the notes here. We need a way to be able to write these systems and talk about these systems and manipulate these systems as efficiently as possible. And so writing them like this can be useful, but it's, we're keeping track of two equations at the same time, and it's kind of clumsy and clunky. And so there's a couple of different ways that we're going to learn how to kind of condense this and rewrite this. And we'll get to that in the next video.